So this is a lecture for Physics 350, where we are in Chapter 6 of Taylor's book on modern physics. And where we left off last time was a review of wave mechanics. Because what we're alluding to is the fact that quantum mechanics is built on wave mechanics. That Schrodinger was able to write his Schrodinger's equation, which is a wave equation to solve for a specific type of wave. In this case, a quantum mechanical wave function. So I'm going to spend some time reviewing waves a little bit. And if you remember, the classical wave equation is a second order differential equation with respect to space minus 1 over the speed of the wave squared times the second order derivative with respect to time. So that's your class. All wave equations pretty much fall into this category. It's a second order differential in space, a second order differential in time, and the factor that is inside it is the wave's speed. Now, Schrodinger's equation is a special type of wave where it only has a first order derivative with respect to time, and that makes it a complex wave equation, but it is still a wave equation nonetheless. Okay, so what we find is if you were to solve this wave equation, you should get something which is a sine or a cosine, right? Because if you take a second order derivative, it returns the function, and the good function that it will return, basically the same function, is the sine or cosine. Actually, it returns the negative of that function in order to cancel on both sides. But anyway, the general solution to any wave is, or general solution to this equation is some amplitude times the sine 2 pi the position over the wavelength minus the time over the period. And I'm writing this as a sine. We could have written it as a cosine, but remember the sine and the cosine are just a phase of 90 degrees apart from each other. So I could rewrite this as a cosine function. Either way, what you get is a periodic function, let's say in space, or a periodic function with respect to time. And it's got both of those elements where by this time most people are aware of what the wavelength is. It's just one cycle in space, and the period is just one cycle with respect to time. Now that makes our equation look pretty, or we can interpret this equation. We can look at it and say, yeah, that makes sense, because essentially what we're doing is just finding one place on this. So we could pick one position right here, and that's just going to be a ratio of the position with respect to the wavelength. So you get this ratio, really it's 2 pi because you have to take into account the radians, or it could be at some time over here where it is a fraction of the time over the total period times 2 pi in order to make it have units of radians. So that's what that means, that we're looking, you're basically, since a wave is repeated cycles, then inside of our sine function, we're just picking different points depending on the ratio of either the wavelength or the period. Now looking at these equations, what we have, we can rewrite this to get rid of, let's say, all those denominators and say that we have a wave number, k, which is just 2 pi over the wavelength. And it's called the wave number because you're essentially saying how many wavelengths are we talking about here. So if 2 pi is a cycle, then we're trying to see, how does that 2 pi fit into the wavelength? So you should call that the wave number. You're counting up basically how many wavelengths would fit in some particular position. the frequency you're probably a little more familiar with, because that's 2 pi over the period, or we know that the linear frequency is 1 over the period, so you have 2 pi times the frequency. So the angular frequency is just those frequencies within the 2 pi radius. Now, we can rewrite our equation then as the amplitude times the sine kx minus omega t. And that's a little easier to carry around with you, having the k's and the omegas, to get rid of some of the 2 pi and all the other clutter that's inside the equation. Now the amplitude is just how high the wave is. So that would be our amplitude A. So if this is a function y with respect to, say, x, the amplitude is just how high it's going to get, how high the wave is going to be. So we're not going to focus too much on the amplitude. So again, this wave number tells us, how many wavelengths are inside a certain range. And so, the last thing is the speed. What we find is that the speed of the wave is the distance divided by the time, or we can write it as the wavelength times the frequency, or we can write this now as, let's see, the wavelength would be 2 pi over k, and the frequency would be omega over 2 pi. So those cancel, and we can now write the wave speed as the frequency divided by the wave number. So all of those things kind of fit together into one nice package. Now, in terms of our quantum quantities, the energy, the quantized energy, we said was h times the frequency. This is Planck energy, or h bar times omega. And the momentum, according to the Broglie formula, is Planck's constant over lambda, or h bar times k. So again, using k's and omegas gets rid of a lot of these denominators that we always have to worry about. Okay, so that's kind of just a review, let's say, of the of our waves. Now, what I wanted to do is move on and talk about something more interesting called Fourier analysis. And Fourier analysis, if I wanted to really summarize it in a sentence, it basically says I can create any function out of sines and cosines. So if we just take one sine like this, and then I add in another sine like this, or another function like that, then if I add those two together, what I basically get is something where I'm adding this point and subtracting this point. So I would usually get something kind of, let's say, small. But then I'm adding these 2 points together here, so then that becomes something much more negative. I'm adding these 2, which then turns out to be something more positive. I add these 2, which becomes negative again. This kind of cancels out. And so I get another function, which I get this different shape. So I can create any function by adding together any number of sines and cosines. So usually the Fourier series is written as the function f can be now written as a sum from 0 to infinity of sines and cosines. Now, what are the A's and B's? The A's and B's are the relative amplitude of each of the different contributions. What the N's give us, the N's tell us how many wavelengths we're including. Because if you look at it, you have something that is 2 pi n over lambda, or nk. So we're adding in what wave number contributions are we going to use. And so we have this equation which essentially says my function now is a0 sine of 0 plus a1 sine kx plus a2 sine 2kx plus plus b0 cosine of 0 plus b1 cosine kx plus b2 cosine 2kx plus So I can keep adding sines and cosines and build up this function. And so what we have is something that looks like this. So here's a game from the PHY350 group at University of Colorado at Boulder, where now I can choose. Let me add in some of these a's. So I can add another function, like another sign like that. Yellow is kind of hard to see. I can add in some green. I can subtract out some blue. I can subtract out some purple. I can add in a little bit of pink, maybe half as much. And what you get is a function that looks like that. So you can play around with this, adding up all of your sines functions right here with different relative amplitudes, and you can make some kind of function that resembles something like this. And that's what a Fourier series does, is the Fourier series adds together all of these sines and cosines to make another function. And of course you can play around with it, but in the end what you get is something, if you add enough of them, what we could get is you can add in enough sines and cosines to make things like a square wave. So if you add in all these sines and cosines, and then it would get a little bit choppy at the top, but what you could is add enough of them in to then make something like a sine wave, which is exactly what a function generator does. If you used a function generator in electronics class, then all it did was keep adding in more and more contributions of sines and cosines until it came up with a periodic function like this. Now what we're going to want to use in modern physics instead is to add them all up such that it cancels a lot of stuff, and what we're left with is a wave that maybe looks something like this. And if we look at that shape overall, it looks just like a blob. It looks just like a little packet, a wave packet it is called. And so this wave packet now is what's going to be used to represent a particle. So the particle is made up of a whole combination of different quantum mechanical waves, and when you add those in, add them together constructively and destructively, what you get is a localized little bundle, which we're going to call a particle. So we'll investigate that a little bit more in the next video.